All right, everybody, let's get into some level one problems. All right. In these level one problems, we're going to show the basic relationship between the different types of energy, kinetic energy and gravitational potential energy, and the total energy when we have energy being conserved. So remember, energy being conserved means that the total energy E, all right, which is the sum of the kinetic energy and the gravitational potential energy, is always going to be the same value. So when we add up KE and GPE at any point when energy is being conserved, it doesn't matter how when those conservative forces are acting, they're not going to change the total energy. They're going to keep the total energy the same. They're just going to change it from one type of energy to another type of energy. So this ball is sitting up at the top of our ramp here, all right? And when it sits at the top of the ramp, it has 100 joules of potential energy and 0 joules of kinetic energy. And so if I'm looking at my total energy here, right? So total energy is Ke plus GPE, or our potential energy, right? Then we would have our Ke of 0 joules, and we have our GPE of 100 joules, all right? And that gives us a total of 100 joules of total mechanical energy, all right? And so that's at the very beginning or at the very top up there. And we have to keep this number the same all the time. That means it's being conserved, all right? So no matter where the ball is along the path, it doesn't matter. We should have the same total GPE, or same total E when we add up our gravitational potential energy and our kinetic energy. So we're going to use this picture to kind of help us out. We're going to ignore the velocities for now, and we'll return to that on a later example and see how that figures into this situation. All right. Okay. So we know that we have 100 total joules of energy. So how does that factor into all of these other places, right? So when the ball is here, we know that it has a potential energy or gravitational potential energy of 50 joules. And we know that our E needs to add up to 100 joules, right? So that means Ke plus GPE has to be 100 joules. That's my total energy, right? And if I have a 50 joules, so half of that is taken up for my gravitational potential energy, that must mean that the kinetic energy must also be 50 joules, so I can keep my total of 100, all right? So that means that my kinetic energy in this case is going to be 50 joules, all right? So that's the basics, all right? We just need to keep the total the same, all right? That's what conservative forces do when they do work. They keep the total the same, all right? And so we're just looking at that total energy, E, Ke, GPE. When we add these two up, what's our total energy each time? Now, as we go from here to here, notice nothing really changes. Yes, it's moving during this time, but it hasn't changed its height. And if it hasn't changed its height, that means its potential energy had to remain the same. That's 50 joules. And if its potential energy remained the same, then gravity didn't really do any work, and here we are with our kinetic energy also staying the same at 50 joules. Again, giving us a total energy of 100 joules. And that's important. We need 100 joules there. Finally, we get down here to the bottom, all right? We have our potential energy, our kinetic energy. How do we find it here? Well, now that we're at the bottom, what's our potential energy? Well, it's going to be 0 joules. It's going to be 0 joules because I have ran out of height. Remember, gravitational potential energy is mass times the acceleration due to gravity times the height. And if we have a height of 0, then guess what? GPE is just 0 joules, all right? So we use that 0 joules there, and since the total still has to be 100, that must mean that my kinetic energy is also 100 joules. And I just want to point something out. Up here at the very beginning, we had a potential energy of 100 joules and a kinetic energy of 0 joules. And what gravity did as this thing went down is it took that 100 joules and changed it from potential energy into kinetic energy. So it didn't lose any energy. All it really did was just take the energy that it had in the form of gravitational potential energy and turned it into kinetic energy instead. Right? So this is the most basic type of problem, just where we keep that total the same. In example number 2, we're going to use the same concept, but in a little different way, all right? So we have a 300 kilogram roller coaster starting from rest at the top of the 30-meter tall hill. And we want to know what its speed is at the bottom. All right, there's a bell. We want to know what its speed is here at the bottom, all right? And so I'm going to start by drawing a picture. And, you know, a roller coaster can do a lot of funny things. And what's really cool about energy is it doesn't really matter what happens in between the starting point and the ending point, all right? Because when conservation of energy is happening, when we only have conservative forces, then the path doesn't matter, all right? The path does not affect it. And that's something that it makes a conservative force special as compared to non-conservative forces. So what do we really have here? All right, we have a starting point, an initial place, and we have an ending point, a final place, right? And at each one of these, we can look at our energy much like we did in that last example. So at the very top here, we have an initial kinetic energy, right? We have an initial gravitational potential energy. Here we have a final kinetic energy, all right? And we have a final gravitational potential energy. And the two of these added together gives us our total energy. So, you know, if I'm just thinking about this part up here, my total starting energy is my initial kinetic energy plus my initial gravitational potential energy. And down here, my total final energy is equal to my final kinetic energy plus my final gravitational potential energy. And I can kind of expand these things, all right? Now, what's interesting here, though, is this actual problem. We have this 300 kilogram roller coaster starting from rest at the top of a 30-meter tall hill. And since it's starting from rest, that means its initial velocity is 0 meters per second, all right? And we know that kinetic energy is equal to 1/2 mv squared, right? So that must mean that if my initial velocity is 0 meters per second, my initial kinetic energy is 0 joules, all right? So that makes this just 0. And all of my energy at the very beginning is just gravitational potential energy. At the end, we've gone all the way down to the bottom, right? And what we've done in that process, all right, is that we've actually converted all of our gravitational potential energy that we started with into kinetic energy at the ending. Because here, all right, we have our final height of 0 meters, right? And that must mean that my gravitational potential energy at the end, right, because we know that GPE is equal to mgh, right? So if my final height is 0, that must make my final gravitational potential energy 0. So I take all of that energy that I started with up here at the top, my initial gravitational potential energy, and I turn it into kinetic energy here at the end. So how do we show this calculation? Well, we want to take into account our initial velocities, our final velocities, our initial heights, and our ending heights, because we want to be talking about gravitational potential energy and kinetic energy. All right, when something's 0, we can go ahead and we can cross it off, and we can show how we use all of this stuff here. So I'm going to leave that height final as 0 meters. My initial height up here, because we're at the top of a 30-meter tall hill, is 30 meters. We also know our velocities, right? Our initial velocity is 0 meters per second. And we know our final velocity is what we're actually looking for here. What's the speed at the bottom, okay? So the law of conservation of total mechanical energy says that when we have conservative forces, that the total energy E is always going to be equal throughout the entire thing. That means our total final energy should equal our total initial energy. And total energy is Ke plus GPE. And that goes for the ending, so that's my final total energy. And this is my initial total energy. Now, we can kind of take it a little bit easy here and we can save ourselves some steps. Because I know that my initial velocity is 0 meters per second, right? And we said that makes my initial kinetic energy 0 joules. So I'm not going to do any substitutions for that. And my final gravitational potential energy is going to be 0 joules because I have a final height of 0 meters. So we can cross things out that we don't need in this equation, but the total is still KE plus GPE. And so that makes my equation KE final should equal my initial gravitational potential energy. And so what I'm going to do now is I'm going to use the equations for kinetic energy and gravitational potential energy. All right? So don't forget, kinetic energy is 1/2 mv squared, and gravitational potential energy is mgh. So I'm going to use that here in my equation. For KE final, I'm going to use 1/2 times my mass times my final velocity squared. And here for my GPE initial, I'm going to use mass times the acceleration due to gravity. And because it's initial, it's my initial height. All right. And from here, I can go ahead and I can substitute all the values that I know. I have a 300 kilogram roller coaster. It's starting from rest, right? We already took care of those zeros. We want to find V final. That's right here, okay? So how do we do it? Let's substitute and we'll solve, all right? You can pause the video now and you can try to solve this yourselves. Okay, so at this point, I would probably simplify my values here a little bit. On the left side, I end up with 150 V final squared. Over here on the right side, this is going to be 88,200 joules. All right. I can go ahead now and I can divide both sides by 150. That cancels my 150 in front of my V final squared. I get 588, but that's still squared, so I'm going to take the square root of both sides. And that should give me my final velocity. Of about 24.2 meters per second. So there we go. That's how we use the law of conservation of total mechanical energy, just to point some important parts out. We always start up here with this equation, E final equals E initial, all right? We always write this equation with our initials and our finals, and this is the step where if something's 0, you can cross it out. If it's not, like we see down here, KE final was not 0 and GPE initial was not 0, then I used the equations 1/2 mv squared when it was kinetic energy and mgh when it was gravitational potential energy. And then from there, all I had to do is substitute and solve. All right, so that's example number 2. Good luck with the first sets of example, or the first sets of problems, and then you can move on to level 2.